Today we're going to take a look at how to solve equations using exponential functions and logs. Looking at this first example, 16 to the v power equals 67 looks very similar to things we've done in the past, except for in the past we've had our variable as our base and then maybe like a third power up there, in which case we would just take the cube root of both sides. However, when I have a variable as my exponent, I can't take the v root of both sides because you don't know what that value of v is. So you don't know what the v root of 67 is. So in order to solve this problem, we're going to try to convert it to log form and see if that gives us something that we can work with. So 16 is my base. So I have log base 16, come across the equal sign. So of 67 equals, back around here, v. So just like that, we have our variable isolated. Log base 16 of 67 is actually something that we can type directly into our calculator. So I have Desmos open right here. If you click on the functions button in the bottom right, and you click on miscellaneous at the top, in the next to the bottom row, in the middle, you see log base A. So if you just use the one on the left that says log, that's automatically a base 10 and you can't change it. So if you use log base A, it's going to give you that little subscript where you can type 16. And then we want to arrow over to our parentheses and type a 67. So log base 16 of 67. And that gives us an answer of 1.52 when we round. So we can say v, is approximately 1.52, which means that if I raised 16 to that power, we would get 67 as our answer. And we can type that in. It's not going to give us an exact 67 because, as you know, we did round that decimal, but it gives us 67.6. So very close. Okay, let's look at another one. I've got 9 to the n plus 10 power plus 3 equals 81. So once again, I'm going to need to isolate my exponential term first. So we're going to isolate this by subtracting 3. So I have 9 to the n plus 10 power equals 78. Okay, I cannot subtract that 10 from the exponent because it's stuck up there as an exponent. So we consider that our exponential term being isolated. So I'm going to rewrite this in log form. So right here, I've got log base 9 of 78 equals up here n plus 10. So you could go ahead and type in log base 9 of 78 to your calculator and get a decimal and then subtract the 10. Or we can, not with the eraser, Miss Hoke. Or we can go ahead and subtract 10 right now. We just need to make sure that it does not end up inside of our log. So log base 9 of 78 with a minus 10 on the outside. And now we have our variable n isolated. So coming back over here, I want my log base A out of my functions menu. So log base 9 of 78. And then we want to close that parenthesis and put a minus 10 on the outside. So we see that that's negative 8.02 when we round it. Let's come up here and look at example 3. 4 times e to the 2 minus 2n minus 9 equals 4. So looking here, this e value with its exponent is our exponential term. The 4 out in front is a coefficient that we're going to need to get rid of before we change it to log form. So I'm going to start by adding 9 to both sides. So I have 4 times e to the 2 minus 2n power equals 13. We're going to divide both sides by 4. And I'm just going to leave that as 13 over 4. That's fine. So I've got e to the 2 minus 2n power equals 13 fourths. So now that I have my exponential term isolated, I'm going to go ahead and change it into to logarithmic form. With a base of e, that means we're using our natural log. So we have natural log of 13 fourths, because we come across, equals 2 minus 2n. So at this point, you could go ahead and figure out what the log of 13 fourths, the natural log of 13 fourths is. I'm going to go ahead and subtract 2 to get rid of that. So I have the natural log of 13 fourths with a minus 2 on the outside equals negative 2n, and then we can divide by negative 2. So like I said, you can type it into your calculator and get a decimal and then move everything else away, or you can just type it all in at once. I'm going to type it in just like that. So we're going to go ahead and type the whole thing into Desmos. I need to make sure and put my numerator in parentheses. Okay, natural log is on the first column right above log. So natural log of 13 over 4. We want to close that parenthesis out to close off our natural log. Minus 2 is the other part of my numerator. And then we want to divide all of that by negative 2. So we made it look exactly like it did in our problem. And I get 0.41 as my answer. So we can say n is approximately 0.41. Okay, if we wanted to plug that into our original equation, we could. We would just plug it into this n and see that it equals approximately 4, because remember we rounded our answer. Okay, let's look at the second type of solving that we're going to do. So this says solving exponential equations by changing the base. So for these, we can't get them into logarithmic form because we have 2 exponents. So we can't say log base this and log base that, or combine 2 logs together. We don't know those rules yet. So here we're wanting to set our exponents equal to one another, and we can only do that if the bases match. So this first example, we've already got the bases matching. So this says 5 to some power equals 5 to some power. So for example, let's say that that power is a 3. So the only way 5 to the 3rd power is going to equal something else is if it's also 5 to the 3rd power. When we have the same bases, the exponents have to be equal in order to create an equivalent statement. So once we get our bases to match, we just take our 2 exponents and set them equal to one another. So this would be set up 3 minus 2x equals x. So from here, I'm going to add the 2x. So I get 3 equals 3x. And when I divide, I find out that x equals 1. Okay, if we went back up to our original problem and plugged in a 1, so 3 minus 2 times 1 is 5 to the 1st power. If I plug in a 1 here, it's 5 to the 1st power. And 5 does equal 5. That makes a true statement. So that one was easy since our bases already matched. Now, when the bases don't match, we're going to have to think about how we can rewrite them to make them match. So another way we can think of 25 is 5 to the 2nd power. So 5 to the 2nd power and 25 are equivalent. Okay, I still have this x power out here though. I'm just replacing 5 to the 2nd power for the 25. And then I'm going to bring down the other side, 5 to the x plus 1 power. So if you remember earlier in the year when we did exponent rules, if I have a power raised to a power, that means that we can rewrite it as multiplication. So this is 5 to the 2x power, and that's equal to 5 to the x plus 1 power. So now that we've got bases that are the same, our bases are the same. We have a 5 on both of them. We're going to set our exponents equal to one another. So I have x plus 1 equals 2x. When I subtract x from both sides, I find out that we have 1 equals x, or we could write it as x equals 1. We could also write it as a solution set like this. So both of these first answers happen to have x equaling 1. That's not always the case. Of course, we could go plug it back in up here. So if I plug a 1 in here, 1 plus 1 is 2. So 5 to the second power is 25. And then if I plug in a 1 over here, 25 to the first power is also 25. So we get an equivalent statement. Okay, coming down here, I've got 16 to the x plus 1 power equals 4 to the 4x plus 1 power. So I know that I can rewrite 16 as 4 squared. And then that just replaces this. I still have x plus 1 power equals 4 to the 4x plus 1 power. So here I know that if I have a power raised to a power, I'm going to multiply these two things together. So that means that the 2 has to multiply by the x and by the 1. So when I distribute that, I get 4 to the 2x plus 2 power equals 4 to the 4x plus 1 power. So now that we have the same bases, we're going to take the two exponents and set them equal to one another. So I have 2x plus 2 equals 4x plus 1. I'm going to subtract the 2x, cancel that, subtract the 1, cancel that, and I get 1 equals 2x. And when I divide by 2, I find out that x equals 1/2. If I go back up to the top and plug that in, if I have a 1/2 here, I get 16 to the 3/2 power. If I have a 1/2 here, 4 times 1/2 is 2. So I get 4 to the 3rd power. So 16 to the 3/2 and 4 to the 3rd. If I type that into my calculator, 16 raised to the 3/2 power is equal to 64. 4 raised to the 3rd power is also 64. So we get an equivalent statement. Okay, looking at this next one, 32 to the x power equals 8. I can't write something with a base of 8 to get me 32. I can't write it as 8 to the first power or 8 to the second power or anything like that. So we're going to have to think of something that we can change both of our bases to get them to match. So I know that I can write 8 as 2 to the 3rd power. And I'm going to see if I can get 32 using 2's. So I know 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. So I see right there that I have 5 2's multiplied together to get me a 32. So I can write 32 as 2 to the 5th power. Remember, I just replaced the 32 with this. So I've still got this x up here at the top. So this is really 2 to the 5x power equals 2 to the 3rd power. So now we can take these exponents and set them equal to one another. 5x equals 3. When I divide by 5, I find out that x equals 3/5. So if I typed in 32 to the 3/5 power, it would give me a value of 8. And that is a true statement. Okay, let's try one more. So we know, oh, this one's going to be easy because we already have our list of numbers right here. So I can write 16 as 2 to the 4th power. and then I still have x plus 4 up here. I can write 32 as 2 to the 5th power, and then I still have 2x minus 10 out here. So I'm going to go ahead and multiply these exponents out. So I've got 4 times x and 4 times 4 gives me 4x plus 16. Over here I have 5 times 2x, 5 times negative 10. So that gives me 10x minus 50. I'm going to go ahead and I'm going to just move my x's to the left, my constants to the right. So I get negative 6x equals negative 66. When I divide by negative 6, I find out that x equals 11. If we plugged that back into our original equation, if I had an 11 right here, I would get 16 to the 5th power equals an 11 right here would be 32 to the 12th power. Oops, my 15 didn't write. So 16 to the 15th power equals 32 to the 12th power. 16 to the 15th is a very long number in exponential form, or sorry, scientific notation. Okay, and we get the same very long number in scientific notation. So that times 10 to the 18th would mean we move our decimal place 18 places to the right. Doesn't matter what we get as long as it's an equivalent statement. Okay, so that is how to solve exponentials by changing the base. So that's when we have 2 exponential pieces within the same problem. Okay, up here at the top, we only had 1 exponential piece, so we were able to change it to logarithmic form. So now we're going to solve logarithmic equations by using a couple of different methods. So on this first one, we see log of 5x is equal to log of 2x plus 9. So since these both have the same base, just like with our exponents, we're able to take what's inside and set it equal. So we have 5x equals 2x plus 9. Subtract 2x from both sides, and we get 3x equals 9. Whoops, not divide by x, divide by 3. And we find out that x equals 3. So if I plug a 3 in, I get 15 on the left and 15 on the right. So log of 15 is equal to log of 15. That is a true statement. Okay, this next one we have log of negative m plus 2 equals 4. So the first thing I'm going to do is isolate my log by subtracting 2. So I have log of negative m equals 2. And at this point, we're going to change it into exponential form because I don't have 2 logarithms in the same problem. So we're going to do it by changing it to exponential form. So this has a base of 10. So my exponent has a base of 10 to the 2nd power equals negative m. So I know 10 to the 2nd power is 100. And then to get rid of that negative, I'm going to divide by negative 1. So I have m equals negative 100. So when you're plugging this back in, you're not doing the log of negative 100. You're plugging it into a negative m value. So you would really plug it in as log of negative m. So log of negative 100, because you have that negative in front of your variable, and then your variable also has a negative. Okay, we could go into Desmos and type that in just to check our answer, but we will see that it does indeed work. So this is just the common log. I can use the regular log button of negative 100. We see that we do get an answer of 2. Okay, I'm not going to work through this one, but natural log, remember that's like a log with base e, so those 2 bases match. You're able to just set your 2 values that are inside the parentheses equal to one another and solve. Okay, let's look at this one where we have a quadratic that we're going to be dealing with. So here we have the same base because they're both base 10. They're both a common log. So I can take 16 plus 2b, set that equal to b squared minus 4b. So since we have that b squared term, we're going to need to get everything to the same side. We're going to need to get it in standard form. So I'm going to go ahead and subtract the 2b and the 16 and get everything over there with the b squared. So I've got b squared minus 6b minus 16 equals 0. So I'm going to factor this. So I want two things to multiply to be negative 16, add to be negative 6. So I've got x minus 8, x plus 2 equals 0. And when I set those each equal to 0 and solve, I find out that x equals 8 and x equals negative 2. So we want to make sure that we plug these in and get a true statement. So if I plug an 8 in right here, I have 16 plus 16, which is 32. And then if I plug an 8 in over here, I've got 64 minus 32. So that also gives me log of 32. So go ahead and type that in. Just make sure that 32 is a valid value. So we have log of 32 and we get 1.51. So since both sides are equivalent to that, we know that that is one of our answers. So we know x equals 8 works. Okay, let's plug in a negative 2. If I plug in a negative 2 right here, I've got 16 minus 4. So this is going to be log of 12. If I plug in a negative 2 on the other side, I've got negative 2 squared, which is 4, minus negative 8, so plus 8, which is also a 12. Okay, so then we can come over here. We can type in log of 12 just to make sure that that's going to work. Whoops. So I have log of 12. Yep, 1.08. Okay, so this particular equation has two answers. And of course, we can write them as a solution set. So negative 2, 8. Okay, let's look at this last one. Negative 2 log base 5 of 7r equals 2. So I'm going to start by isolating my log. I know since there's only one log in this equation, we're going to have to change it to exponential form. So I have log base 5 of 7r equals negative 1. So here I'm going to say, start with my base, 5 to the negative 1 power equals 7r. And then I'm going to divide by 7. So I'm going to type into my calculator 5 to the negative 1 divided by 7. 5 to the negative 1 power divided by 7. So that gives me an answer of 0.03. So we can say, whoops, r equals 0.03. Okay, when we plug that back in, I have negative 2 log base 5 of 7 times r. So 7 times 0.03. That gives me an answer of 1.94, which is extremely, extremely close to this 2. So that's just because of rounding issues.